Hi, my name is Christensen from KGSEA Math Circle, and today my lecture will be covering some mathematical topics in chess. So what is chess? Chess is a very famous board game created in India in the 6th century. Its objective is to trap the opponent's king such that it has no more legal moves. It's very popular. More than 500 million people play it around the world. And thanks to its long history, chess has had no shortage of mathematical interest and research surrounding it. In this lecture, I aim to explore some mathematical concepts in the game of chess. So first, I'd like to talk about Shannon's number. In 1950, computer scientist Claude Shannon estimated that there were 10 to the 120 possible games of chess. This result was obtained by assuming an average of 30 legal moves in a given position and assuming an average of 40 moves in a game, with both players making a turn in one move. This number is actually greater than the number of atoms in the universe. So you can see here, this function grows very quickly. This estimate's not entirely accurate, however, as it considers various illegal positions and ignores some legal combinations. Additionally, the estimate assumes only the game to be only 40 moves. However, in actuality, a chess game can theoretically stretch on for over 11,800 moves before terminating due to the 50-move rule, where if both players do not move any major pieces in 50 moves, it is called a draw. Monte Carlo simulations estimate the actual number of possible games to be over 10 to the 29,241. That's not a factorial, by the way. Shannon's number was sort of devised to demonstrate that brute forcing the calculation was not possible. Another topic I want to be covering is combinatorics in chess. Chess lends itself very well to combinatorics, and here are a few select problems. So A, what is the maximum number of rooks able to be placed on a standard chessboard such that none of them are threatening each other? Remember, a rook can threaten anything that is on the same row or column as itself. So in the drawing to the left, to the right, it would be able to take the black bishop and the black pawn. B, how many ways are there to satisfy the conditions of A? And C, how many ways are there to satisfy A without having any rooks on the main diagonal? So from A1 to H8. So if you're watching this at home, please pause the video and attempt these problems. And also another exercise for you would be to repeat the exercise for the other pieces, like the bishop and the queen and so on. So now I'll be going into the solution for these questions. So it's first, number A, since each rook attacks one line, a row, or a column, and there are 8 lines on a chessboard, there are a possible maximum of 8 rooks on the board, and the existence of a valid combination can be easily proven by placing 8 rooks along the diagonal, like you see at the right. So now question B, since each rook takes up one row, the rook on the first row has 8 possible columns it can occupy. The second rook has 7 since it cannot threaten the first rook. And now it's easy to see that the total number of combinations will be 8 factorial, or 40,320. So now C, we have a restriction that the rooks can't lie on the diagonal, the main diagonal, shown by the orange arrow. And this problem can be solved using the derangements of a set. A derangement is a permutation in which no element appears in its original position. And if we assign the rook in each row a number, and if it lies in the column with the same number, it is on the main diagonal. Therefore, the problem is asking us to find the derangement of 8, which can be calculated recursively using the formula, the derangement of n equals n minus 1 times the derangement of n minus 1 plus the derangement of n minus 2, which gives 14,833 possible ways. There's also a closed form expression for this, but for small values like 8, it's probably faster to use the recursive formula. And so I encourage you to repeat this exercise with the other pieces if you want some more practice with combinatorics and counting. But without further ado, I'll move on to the next topic, which is the Knight's Tour. It's a very famous math problem related to chess. The knight moves in an L-shaped motion, going 2 spaces in one direction and 1 space in another, as shown to the right. And the knight tour asks whether it is possible to visit all squares exactly once on an m by n board and return to the starting square. The existence of a closed knight's tour, meaning that it ends on the same square that it starts in an m by n board with m less than or equal to n, is possible if none of these conditions are met. Number one, m and n are both odd. So that means if m and n are both odd, then a closed knight tour is not possible. M equals 1, 2, or 4, and m equals 3, and n equals 4, 6, and 8. So if you're curious, I encourage you to try proving this yourself, but today I'll be proving some of these restrictions. So the first one, m and n are both odd. The knight's tour is a variety of the Hamiltonian path problem in graph theory. And since we have to return to the starting square, this is a cycle, not a path. A path is a knight tour that can end on any node, not necessarily the starting one. And additionally, we know that the knight's tour is a bipartite graph because the knight always alternates between black and white squares, and these can never be adjacent. This is also referred to as the chameleon property of the knight. Since a bigraph always has an even number of nodes in a cycle, if m and n are both odd, the total number of nodes is also odd, which makes the closed cycle impossible. Now I'll prove the second restriction. M cannot be 1 because the knight would not be able to move. M cannot be 2 either because the knight would only be able to access half of the squares. The proof for m equals 4 is a bit more complicated. In a 4 by n grid, you can think of the red dots as you see on the right, symbolizing the outer squares, and the blue ones in the middle inner squares. The tour has to alternate between red and blue because else there's going to be a few red or blue ones left over. Therefore, all red and blue squares have to be black and white because the knight also alternates between black and white squares. However, this is not the case because we have both black and white squares that are red on the outside. Thus, by proof of contradiction, m cannot be 4. And I leave the proof for condition 3 as an exercise. If you're familiar with graph theory, then I urge a hint would be to think about the properties of a Hamiltonian path. So another cool thing about knight's tour is that Euler actually created a semi-magic square that follows the path of a knight tour. So if you look at the square to your right, you'll see that the top left corner starts with 1, and then you see up 2, 3, and 4, so on. And each row and column in the magic square adds to 260, and each quadrant sums to 520, and each half row and column and quadrant sum to 130. But it's not a legitimate magic square because the diagonals don't add up to 260. So that's all I have for you today. Thanks for listening. And I hope that my presentation has sort of encouraged you to explore and look for mathematical concepts in areas that might not necessarily be related. Yeah, thank you for listening.